Before we get started, if you haven't subscribed to the channel, please consider subscribing. In this video, we are going to take a look at the effect of omitting a regressor on the bias and standard error of the OLS estimator. So essentially what we'll be doing is we'll do a simulation study using R, where we will see what happens when we drop one of the covariates or one of the dependent variables, and how does that affect the bias and the standard error of the OLS estimator. First is we set up some global options. We are basically here making sure that it only prints the results up to 4 decimal points or 4 digits. And whenever we have a very large output, it only prints up to 20 units. And we are also defining a function. This is basically the OLS estimator, and we are basically defining this by ourselves. So this is basically x prime x times x prime y, and this solve is basically R's way of saying inverse. So this part here is x prime x inverse 1, and this part here is x prime y, and these percentage signs and then the multiplication sign, this is basically matrix multiplication. And then we are going to return the coefficients, which is basically the solution of this operation. All right, step 1 is we set up the parameter values, we set up some seed, and then we set up the sample size to be 100, k is equals to 2, so number of coefficients, and r is equals to 0.9, which is the rho. Now we wrap the simulation in a function so that we can repeat it later on. So part A is we are defining a function that takes 2 arguments. N is the number of samples, r is the correlation coefficient. Step 2 is we create a matrix of n rows and k columns with a random normal variable, mean 0, standard deviation 1 for each of the individual ones, right? Okay, sample data is equals to matrix, r normal, so we are taking random draws from a normal distribution, n times k, mean 0, standard deviation 1. Okay, so this is the first step. Next step is we define a 2 by 2 covariance matrix, because again, remember, we need to generate the data x1, x2 in a way that they are jointly correlated with this covariance. And so we'll be using Cholesky decomposition to basically generate the data in this particular format. Okay, so we define the covariance matrix, which is 1 and then 0.9, which is r, and then 0.9 and then 1. Number of rows is 2, number of columns is 2. So this is basically this particular matrix that we are defining. And then we are using the Cholesky decomposition on this particular matrix, sigma, that we just defined. And then we are defining the x variables, the dependent variables, as matrix, sample data, matrix multiplication of the Cholesky decomposition that we've done. So the product of the random draw and the Cholesky factors that we have estimated, this is going to give us our x1 and x2 variables that are going to be correlated just like this way. Okay, and then we generate a matrix of n random normal variables for the error terms. So these are the u's, and then the y's are the dependent variable y, right? And that is basically x1 plus x2 plus u. And finally, we are defining this whole thing as a data frame, right? So the data frame has columns of y's, columns of the x1 and x2, which is here in this object x, and then the columns of the errors, which are in the object us or us. And then we are giving names to each of the columns. So dependent variable x1, x2, and then u. All right, and then this whole thing is wrapped in a function, remember, and then it's going to return us this whole thing output, this object. So this makes it simple for us. So every time we iterate or we need to simulate, we can just call this function, and this function is going to do the thing for us. It's going to do the random draw, it's going to do the Cholesky decomposition, it's going to multiply the Cholesky factors with the random draw to give us the x1 and x2 in having this particular covariance matrix, and then it's going to create the dependent variable y, put all of them together as a data frame, and then just throw us the output. So we don't have to do this every time. All right, now we generate the simulated data. So y is equals to as matrix. So we define the dependent variable, we define the independent variable, the regressors. And for the second regression, where we are regressing with x1 alone, this is for that one. Next part is we write a function to calculate the standard errors of the estimators. Remember, we have already written a function called OLS that estimates and returns the coefficients. So now we want to write another function that will simplify the process for us and just return the standard errors. All right, so we can see first we get the residuals, which is the actual values of y given minus the predicted values of y using the OLS estimators. And then we are calculating the degrees of freedom, and then we are computing the covariance matrix of the OLS estimates. Again, this is the usual formulas that we have derived in our theory parts. And then square root of the diagonal matrix of this object beta covariance. So we're basically making this diagonal matrix using the covariance that we're estimating. And then we are returning this thing through this function, which is the standard errors. All right. Now let's write a function that calculates the bias and the standard errors. It will be useful for repeating the analysis for the 1000 times. So again, we're wrapping every step together in functions so that we can just put them in our iterations, and they'll just do all the work every time iterating. So first is we define a function to calculate the bias and standard errors. So bias is basically the difference between the true and the estimated. So beta hat is equals to OLS of xy. Remember, beta hat is the regression of y on x1 and x2, and beta tilde is regression of y on x1 alone. And this is exactly what we do. Beta tilde is regression of x1 alone on y. And then bias of beta hat is the true value 1 minus beta hat. So we are assuming that the true value is 1. Bias of beta tilde. And then we look at the OLS standard errors using this standard error function that we just wrote. So here it is. And then we look at the standard error of the other one, for the tilde one, standard error of beta tilde. And again, if you looked at my other videos, how we can display the output. So we are basically creating a list which basically contains all the objects that stored the coefficients, the biases, and the standard errors, and representing the whole thing as a list. And this is going to return the output list. Amazing. Now we can start basically calculating all of the coefficients, their biases, and their standard errors, and then we can repeat them as many times as we need to. All right, this is the first iteration. We can see that beta 1 hat is 1.1. Bias of beta 1 hat is 0.1. Of course, if the true is 1, the difference is 0.1. Standard error is 0.22. Then if we look at beta tilde, the estimate of beta tilde is 2.02 and the bias is 1.02. It's a very large bias when we drop one of the covariates, and the standard error is 0.1. So it's a much smaller standard error than what it should be in the actual. Now let's repeat this 10,000 times, 10 to the power 3 times, which is 1,000 times. And we are basically going to create objects that are going to store the results for each iteration. And this is the loop to run that. So every time it's going to generate the data. So the data generation part we have wrapped in this function called part A. We are assigning the models and the regressors from the data that's generated, and then we are using the part B formula that we just function that we just wrote, which basically estimates the OLS estimators, and then we have the biases here, and this is iterating from 1 to R, where R is 10 to the power 3, and then saving the values in each of these objects. All right. Now the average bias of beta hat is 0. That is expected. The average standard error of beta hat is 0.23. All right. The average bias of beta tilde is 0.9, and the average standard error of beta tilde is 0.11. So we are seeing that as we simulate 1,000 times, the average bias of the OLS estimator goes closer and closer to 0. The standard error stays similar to previous. However, after dropping a regressor, the average bias actually increases, but the average standard error decreases. So this is a good lesson for us, that whenever we drop important covariates, basically whenever we have omitted variable bias, we are not going to have unbiased regressor, unbiased coefficients, and we may see a smaller standard deviation or standard error, which is not the true representation. All right, lastly, what happens if the covariance between these two covariates is set to 0? We repeat parts A to C, which is set R equals to 0, which is the row here, and we can see that the average bias of beta hat is 0. Again, this is the OLS one. Average standard error is 0.1. But now the average bias of beta tilde is 0, and the average standard error is 0.14. So now that the two regressors are not correlated and orthogonal to each other, so now they're basically perpendicular to each other, they're unrelated, hence dropping a regressor that has no effect on the bias. So basically what's happening is now that the covariates are are not correlated. So if we omit any of the covariates that are uncorrelated, that is not affecting our coefficient estimates, both in terms of bias as well as in terms of variability. So this is a very good way to basically numerically see what happens when we have an omitted variable bias in OLS estimates. And the key takeaway from here is that whenever the covariates are correlated strongly or reasonably in a medium way, then dropping the covariates are going to affect our estimates. But if the covariates are uncorrelated or very weakly correlated, then they are not going to affect the estimates of our bias as well as the standard errors. If you like my videos and find them helpful, then please support my work by subscribing to the channel.